Hi again, this is Tzvi Rosen here with the second lecture in the Calculus 2 course. Today we're going to be talking about integration by parts, and that's featured in chapter 7.1 of Stewart. Integration by parts is a formula that we derive from the product rule of differentiation. If you'll recall, the product rule says that the derivative of the product of f and g, two functions of x, is equal to f times the derivative of g plus g times the derivative of f. Integrating both sides and applying the fundamental theorem of calculus, we find the following. So first we integrate on both sides, and then going from line 1 to line 2, we apply the fundamental theorem of calculus, which says that basically integration and differentiation are inverses of each other. So if you take a derivative and then the integral, you get the original function. Note that even though this is an indefinite integral, we do not pick up a constant of integration. And the reason for that is that we can just absorb any constants of integration onto the other side of the equation. I'm just going to write that as a note here. Constants of integration is absorbed on the left side, on the right side. Okay. So now we have that f of x times g of x equals the integral of f dg dx dx plus g df dx dx. We're going to move this integral over to this side of the equation by subtracting it, and then swap sides of the equation, and we get the final line, which states that the integral of f g prime dx equals f times g minus g times f prime. Okay. An alternative notation that is a bit more common for this formula is the integral of u dv is equal to uv minus the integral of v du. Here dv means the derivative of v with respect to x times dx, and du means the derivative of u with respect to x times dx. Let's do an example to clarify the notation. So we have u equals x squared and v equals 1 over x. Okay, so as we just mentioned, du is equal to the derivative of u with respect to x times dx. So we get 2x dx, whereas the dv is equal to the derivative of v with respect to x times dx, so we get dv equals minus 1 over x squared dx. Okay, so now our formula for integration by parts was the integral of u dv equals uv minus the integral of v du. In our case, this means the integral of x squared times minus 1 over x squared dx is equal to u times v, so that's x squared times 1 over x minus the integral of v du, which is 1 over x times 2x dx. Okay. So simplifying this equation a bit, we have the integral of x squared times minus 1 over x squared is minus 1. Minus 1 dx is equal to x minus the integral of 2 dx. Okay. Now, this equation looks believable, but let's just actually compute the integrals to make sure this is correct. Integral of minus 1 dx is minus x plus c and that's, we say, is equal to x minus the integral of 2, which is 2x plus, let's give it a different constant of integration, so we'll call it c prime, or let's make it c tilde. I like tildes. X minus 2x plus c tilde. And we can see x minus 2x is minus x, and we have minus x plus a constant on both sides of the equation. So this confirms what we know about integration by parts. But it's not particularly useful. All of the things in this equation up here, this equation, we knew all of these integrals. You know, it's just the integral of -1 and the integral of 2. These are not complicated. So doing this process doesn't teach us anything. But let's do the integration by parts formula in a more useful example. So this time we're going to let u be simply x, and v will be sine x. Okay? In, using the same formulas as before, du is the derivative of u with respect to x, so just 1 times dx, and dv is the derivative of sine x, which we know is cosine x, dx. And let's write out our formula for integration by parts. Integral of u dv equals uv minus the integral of v du. And plugging in what we've written so far, we get the integral of x cosine x dx is equal to x sine x minus the integral of sine x dx, okay, because du is dx. So what we'll notice is that this is an unknown integral. Oops. This is an unknown integral. Looking at this in advance, I wouldn't know how to do this integral because this isn't one of the elementary functions whose antiderivative we know offhand. This, on the other hand, this is known, right? We know what the antiderivative of sine x is. So what we have is a formula for an unknown integral in terms of a known integral, and we can simplify it. The integral of x cosine x dx is equal to x sine x. Okay, and then we get the antiderivative of sine x is minus cosine x, so that becomes plus cosine x plus c. Okay, and this is a new formula which we've derived from integration by parts. So this is pretty cool. We were able to get a formula for this funny looking integral, which looks a little bit like a product, using integration by parts. But we came into it knowing what u and v were. We knew that u is x and v is sine x, and we just plugged into the formula. But if I come to an integral like this, how do I know what to set as u and v? Okay, that's the next question we ask. How do we choose u and dv? Intuitively, u should be the function that we most want to differentiate in order to simplify our expression. Okay, so for example, if we have a logarithm in our integral, so ln of x, when we take the derivative of that, it becomes 1 over x. And that can be much simpler, right? Logs don't play too nicely, but 1 over x can cancel with polynomials, for instance. Okay. Similarly, inverse trigonometric, when we take a derivative, let's say arctangent of x, the derivative of this is 1 over 1 plus x squared, which is much simpler. This, in an expression, would be hard to, it wouldn't interact nicely with much of anything, but this, you can do a u substitution. There's lots of tools at our disposal. Okay, similarly, when we have an algebraic function, x cubed plus x squared plus 1, okay, and here we're talking about things like polynomials, rational functions, powers of x, things like that. When we take the derivative, we get another polynomial, but it's a simpler polynomial. Right now, the highest degree that appears is strictly lower, and one of the terms vanished altogether. Okay, so for this reason, it's simplified. It doesn't simplify as drastically as log to 1 over x or arctangent to 1 over 1 plus x squared, but it still gets simpler, which is nice. Trigonometric and exponential, neither of these simplify too much. We have sine x becomes cosine x, and that's not really changing much. It's a different trig function, but it's the same complexity, and if you keep taking derivatives, you're just going to get back to sine. Similarly, e to the x, when I take a derivative of that, I just get e to the x back, and that doesn't simplify at all. It doesn't change anything. So for that reason, we'll always want to start at the top when we're picking the thing we want to differentiate. Okay, look for the logarithm first. That's what I want to differentiate. If there's no logarithm, I'll probably want to differentiate an inverse trig function, etc., going down the list. And the mnemonic is liate, and that's for the order in which we'd rather differentiate. Okay, so let's take an example. Compute the integral of x ln x dx. Okay, so I know that I'm going to, so first let's classify the different parts of this. We have x, this is an algebraic function, which is an a, and ln of x is a logarithmic function, which is an L. Okay, L comes before A. Okay, for that reason, we'll want to make our u be equal to ln of x. Given that our u is ln of x, our dv is left as x dx. Okay. Now, taking the derivative, we find du is equal to 1 over x dx. And taking the integral, or the antiderivative of dv, we get v equals x squared over 2. Now let's plug this into our integration by parts formula. Again, it's integral of u dv equals uv minus the integral of v du. And what we find is the integral of x ln x dx, okay, which is the integral that we're interested in computing, is equal to x squared over 2, that's v, times ln x, which is u. And I only switch the order for aesthetic reasons. I like seeing the log at the end of the expression, minus the integral of v du, which is x squared over 2, times du, which is 1 over x dx. Okay, this is x squared over 2 ln x minus the integral of x over 2 dx. Okay, and I will give us an extra page. Okay, so we had x squared over 2 ln x minus the integral of x over 2 dx. Okay, this antiderivative is x squared over 4 plus c. We get x squared over 2 ln of x minus x squared over 4 plus c. And this is our answer. Okay. If you want to be extra careful, you can pause the video here and take a derivative of this expression, you should get the expression x ln x. Okay. So this was an example of applying integration by parts to solve an integral that we're interested in. How about the integral x e to the x dx? Okay, well, this again is an algebraic, and this is an exponential. Okay, if we think about liate, a is greater than e, so we want our u to be the algebraic function. So take let u equal x, then we take, that means that dv equals e to the x dx. Taking the derivative of u, it's just 1, so that's dx. And v will be e to the x because the integral of e to the x is just itself. So let's plug back into the integration by parts formula. We have integral of v du equals, u dv. Let me just rewrite this. Thank you. Integral of u dv equals uv minus the integral of v du. Plugging in what we've found so far, integral of x e to the x dx equals x e to the x minus the integral of e to the x dx. Okay, this integral is just e to the x again. So we get x e to the x minus e to the x with the constant of integration plus c. Another way we could write this, that would be fine to stop if you'd like, but this is, we can factor this a bit, x minus 1 e to the x plus c. Okay, pretty straightforward. Okay, so all of that was done with the indefinite form of the integration by parts formula, but you can also do this with bounds. So if you take the definite integral from a to b of u dv, then that equals uv evaluated at b minus the evaluation at a minus the integral from a to b of v du. Okay, let's see that in action. Suppose we want to compute the integral from 0 to 1 of x sine x dx. Well, let's figure out which of these we want to set as our u and which is our dv. X, again, is an algebraic function, which is a, and sine x is a trigonometric function, which is a t. A is greater than t, so we take u to be a. U to be x, rather, our algebraic function. Let u equal x, which means that dv equals sine x dx. Okay, and that means that du is dx, and v is equal to minus cosine x, which is the antiderivative of sine x. Okay, now let's plug this into our definite form of integration by parts. We have the integral from 0 to 1 of u dv, which is x sine x dx, equals u times v, which is minus x cosine x, evaluated from 0 to 1, minus the integral from 0 to 1 of v du, which is minus cosine x dx. Okay. Well, let's evaluate at the endpoints. When we take x equals 1, we get minus 1 times cosine of 1, which I'll just write as minus cosine 1. And that's some irrational number that we don't have to worry about. And we can subtract from there the value at 0, which because we have a factor of x here is just 0. Okay, so that's this part. And then the two minuses cancel here. So we have plus this the integral of cosine x. Well, we know that's just sine x. So we take sine x, and it's going to be evaluated at the endpoints 0 to 1. Okay. So this equals minus cosine of 1 plus, and this is sine of 1 minus sine of 0, which is 0. Or in summary, this can be given by, the answer can be written as sine of 1 minus cosine of 1. Okay. So that's the basics of integration by parts, but integration by parts can get more complicated. And here are, I think, the three main ways that it gets more complicated. The first is repeated integration by parts. What happens here is that after you finish the first integration by parts, so you plug it into the formula, you run it through, then you're left with an integral in there that you need to apply integration by parts to again. Okay? So that can be frustrating, but it's the right way to do the problem. The next kind is cryptic integration by parts. So usually the way you recognize an integration by parts problem is by seeing a product. Here, the dv is just dx. So it looks like a normal integral that you wouldn't necessarily apply integration by parts to, but it's really an integration by parts problem. That's why I call it cryptic, because it's hidden. The third type is a cyclic integration by parts problem. These are more unusual. This is an integral where after you repeatedly do integration by parts, you get back to the integral you started with, which might seem hopeless, but you can use the new relationships that you learn along the way to solve for the integral. Okay, now we'll do an example of each type. Okay. We want to compute the integral from minus 1 to 1 of x squared e to the minus x dx. Okay, so first step, we can choose our u and our dv. So this is an algebraic function, and this is an exponential function. We know that a comes before e in Lie8. So we're going to want to use we're going to want to use x squared as our u. So let's make u equal x squared, and dv will be what's left, which is e to the minus x dx. Okay, now taking derivatives, we have du equals 2x dx. And taking the antiderivative here, we know that v will be equal to minus e to the minus x. Okay. So now we can plug this into our definite form for integration by parts. We have the integral from minus 1 to 1 of u dv equals uv from minus 1 to 1 minus the integral from minus 1 to 1 of v du. Now we plug everything in. Minus 1 to 1 of x squared e to the minus x dx. This is equal to the function minus x squared e to the minus x evaluated from minus 1 to 1 minus the integral from minus 1 to 1 of v du, which is minus e to the minus x times 2x dx. Okay. So this first part we can plug in and just get the explicit value. We have, when it's evaluated at 1, it's minus 1 times e to the minus 1. So minus 1 over e is another way of writing that. When it's evaluated at negative 1, we have minus the square of negative 1, which is 1, times e to the positive 1. So putting that all together, that's minus e. And so we subtract that. That gives minus minus e, or plus e. And we have plus the integral from negative 1 to 1 of 2x e to the minus x dx. Okay, and I'm actually going to want to take the 2 and put it in front of the integral. Now, looking at this integral, we see this is this is clearly still an integration by parts problem. So let's call this I1. The little subscript. And we're going to compute I1 and then plug that in to get the final answer. So I'll add another page here. Okay, so we need to compute the integral from minus 1 to 1, and this is our I1. Integral from minus 1 to 1 of x e to the minus x dx. Okay, so here again, we'll apply the same tools. This is an algebraic, this is an exponential, and a comes before e. So we have u equals x, dv equals e to the minus x dx. So v is minus e to the minus x, and du equals dx. Okay, plugging this into the formula, the integration by parts formula, we have the integral from minus 1 to 1 of u dv, which is xe to the minus x dx, will be equal to minus x e to the minus x evaluated at the endpoints, minus the integral from minus 1 to 1 of v du, which is minus e to the minus x dx. Okay, again, we just go ahead and evaluate this. We get minus 1 over e minus e, and we subtract, and then because we have actually two minus signs here, that turns into a plus sign, and we're left with the integral from minus 1 to 1 of e to the minus x dx. Okay, this antiderivative, as we've done a few times already, is minus e to the minus x. So this is equal to, let's rearrange, this is, let's make this minus e plus 1 over e plus, and now we'll take the antiderivative here, minus e to the minus x evaluated from minus 1 to 1, and that gives minus e plus 1 over e, and this is minus e to the minus 1, which means minus 1 over e, minus the evaluation at negative 1, which is plus e. Okay, putting this all together, this gives us, so we have a minus e, which cancels with an e, and a minus 1 over e, which adds up with minus 1 over e to give minus 2 over e. Okay, and that's the value for our I1. Looking back up a page, we knew that we wanted to substitute into I1 here. So we can do that now. We get e minus 1 over e from over here, plus 2 times, plus 2 times negative 2 over e. I'm going to adjust this a bit. So this integral will be the I1. This is equal to e minus 5 over e. Okay, so that is our integral. These problems can be a bit long as a result of the repeated integration by parts, but it's totally correct. It's okay for it to take quite a while. Okay, now here's some cryptic integration by parts. Let's say I'm looking at this integral. Compute the integral from 0 to 1 of arctangent of x dx. Okay, so not knowing in advance that this is an integration by parts problem, I would look up, well, what's the antiderivative here? Because it doesn't look to me like a product of functions. But we know this is a cryptic integration by parts problem, so we're going to guess that u is equal to arctangent of x, and dv equals dx. And this means that du equals 1 over 1 plus x squared dx, and v equals x. Okay, so this is useful. Now we're going to plug this into the definite form of integration by parts. We get the integral from 0 to 1 of u dv, which is arctangent of x dx, is equal to x arctangent of x evaluated from 0 to 1 minus the integral of v du, which is x times 1 over 1 plus x squared dx, also from 0 to 1. Okay, so let's go ahead and evaluate. So we have x at the value x equals 1, x arctangent of x is 1 times arctangent of 1 minus 0 times arctangent of 0, which is also 0. And this is equal to pi over 4. And the way that you can remember that is when a tangent is equal to 1, that means the two non-hypotenuse sides of the right triangle are equal, and that only happens when the angle is pi over 4. Okay, so let's just signify that this is for this part. Okay, as for this part, let's call this I1 as before. This is our next integral. We're going to add a page. Here we go. So we want to compute the integral from 0 to 1 of x over 1 plus x squared dx. Okay, and what you might notice here is that there's a really nice u substitution you can do. We're going to call it w because we already have a u involved in this problem. So let's let w equal 1 plus x squared, and dw is equal to 2x dx, okay, just by taking derivatives. So we have x dx here, which means that I can multiply by 1/2 on the outside and 2 on the inside. And then I have 1/2 times the integral of dw over w. And the bounds have to change as well. This bound becomes 1, and this bound becomes 2. Okay, so this integral you should recognize. This is 1/2 ln of absolute value of w, evaluated from 1 to 2, and this gives us 1/2 ln of 2. Okay, so this is our I1. Okay, going back up to the previous page, we can get our formula. So the answer will be pi over 4 from the first part minus I1, which we found was 1/2 ln of 2. Okay, and if you want to get really fancy, you can make this pi over 4 plus ln of 1 over the square root of 2. But that's not necessary. Okay, but this is kind of an interesting answer to get for what seems to be a relatively simple integral. Okay, final category is the cyclic integration by parts, and these are the ones that you go in a cycle. Okay, you start with one integral and it takes you through until you get back to what you started with. So let's start with I1 equals integral of e to the minus x sine of x dx. Okay, so here we have our Lie8 rule. It actually doesn't matter so much in this case, but we will follow the Lie8 rule in any case. So we have a t and an e, and by convention we take t before e. Okay, so we're going to make u equal sine x and dv equals e to the minus x dx, which means du equals cosine x dx, and v equals minus e to the minus x. Okay. So let's plug this into the indefinite form, because we don't have bounds for this integral. The indefinite form of integration by parts. We have the integral of u dv, which is sine x times e to the minus x dx. This is just our I1. So we can even write that over here. I1 will be equal to u times v, or sine x times minus e to the minus x. So minus sine x e to the minus x minus the integral of v du, which is minus the integral of minus e to the minus x cosine x dx. Okay, let's simplify this a bit. I'm going to actually rewrite this so that the e's are in front. Minus e to the minus x sine x plus the integral of e to the minus x cosine x dx. Okay, now here is where we get our I2. Okay, we recognize this also is going to need integration by parts, so let's get started on that. So we have I2 equals the integral of e to the minus x cosine x dx. And let's actually do this on another page. Okay. I2 equals the integral of e to the minus x cosine x dx. Okay, as before, we let u be the trig function. U equals cosine x, dv equals e to the minus x dx, du equals, the derivative is minus sine x dx, and v equals minus e to the minus x. And plugging this in to our standard integration by parts formula, we have u dv, which is again just our I2, e to the minus x cosine x dx equals uv, which is minus e to the minus x cosine x minus the integral of v du, which is integral of minus e to the minus x times minus sine x dx. Okay, so this is minus e to the minus x cosine x. Now we have two minus signs that cancel here, so we have minus integral of e to the minus x sine x dx. And now we notice that this is what we started with. This is our I1. Okay? So looking above, we had, on the one hand, I1 is equal to this plus I2, and I2 is equal to this function minus I1. So let's take what we found above. I1 equals minus e to the minus x sine x, minus e to the minus x sine x. Okay, and that was plus I2. And now we can plug in our formula for I2 in terms of I1. This is minus e to the minus x sine x plus minus e to the minus x cosine x minus I1. Okay? So we can add I1 to both sides of this equation to get 2 times I1 equals minus e to the minus x sine x minus e to the minus x cosine x. Okay, and I'm going to just indicate that this belongs to the previous line. And adding in one more page to finish this up. So we can divide both sides of that equation by 2 to find that I1 is equal to 1/2. And we could even factor out minus e to the minus x from both terms. So we can get, this will be minus e to the minus x over 2 times sine x plus cosine x. And we can't forget our constant of integration. Okay, and that is the integral. So these cyclic problems are very tricky. You need to keep working until you find what you start with, and then you need to express, you need to use the formulas you found with integration by parts. You need to combine them in such a way that you can solve for your original integral. Okay, so those are the three main tough points. You've got the repeated integration by parts, the cryptic integration by parts, and the cyclic integration by parts. There's obviously other wrinkles that can come up. It's possible that after you do integration by parts, you have to do a U substitution, or you have to use some other trick, but those three are the main tricks to be aware of for this section. Okay, we'll stop there.